This is SpaceTime, Series 28, Episode 122, for broadcast on the 10th of October 2025. Coming up on SpaceTime, a potential smoking gun signature for supermassive dark stars, Australia's new lunar rover, and piecing together the early solar system. All that and more coming up on SpaceTime.
Welcome to SpaceTime with Stuart Gary.
Astronomers have identified a new type of star in the very early universe which fits the profile of the long hypothesized supermassive dark star. If they exist, dark stars are very different from the kinds of stars we see in today's universe. The first stars in the universe, so-called population 3 stars, were formed out of the pristine hydrogen and helium created in the Big Bang 13.8 billion years ago. They were extremely massive hot blue stars, formed in the first few 100 million years after the Big Bang. They ended the cosmic dark ages and brought about the epoch of reionization, resulting in the universe we see today. During their lives, fusing hydrogen into helium on the main sequence, and when they died, they produced all the other elements in the cosmos today. But now, new observations by the Webb Space Telescope have revealed that some of the very first stars in the cosmos could have been very different from these regular fusion-powered stars. Webb has identified 4 extremely distant objects which are consistent, both from the point of view of their observed spectra and morphology, with being supermassive dark stars. The study's authors describe supermassive dark stars as extremely bright, giant, yet puffy clouds primarily made out of hydrogen and helium, which are supported against gravitational collapse by the minute amounts of self-annihilating dark matter inside them, hence the term dark stars. These supermassive dark stars and their black hole remnants could be keys to solving 2 recent astronomical puzzles. The larger-than-expected, extremely bright yet compact distant galaxies observed by Webb, and the origin of the supermassive black holes powering the most distant quasars in the universe, black holes which, theoretically, didn't have enough time to get that big. One of the study's authors, Catherine Fries from the University of Texas at Austin, developed the original theory behind dark stars with Doug Spolya and Paolo Gondolo back in 2008, which was reported at the time in the journal Physical Review Letters. In that paper, they envisioned how dark stars might have led to supermassive black holes in the early universe. Then, in a 2010 Astrophysical Journal publication, Fries and colleagues identified 2 mechanisms through which dark stars could grow to become supermassive. They also predicted that these could seed supermassive black holes, powering many of the most distant quasars in the universe. Although dark matter makes up 25% of the universe, its nature has continued to elude scientists. They know it exists because they can see its impact on normal baryonic matter, preventing galaxies from spinning apart as they rotate, and magnifying more distant objects behind them through gravitational lensing. The current thinking is that dark matter probably consists of a new type of elementary particle yet to be observed or detected. While the hunt to detect such particles has been on for a few decades now, no conclusive evidence has ever been found. Among the leading candidates for dark matter are weakly interacting massive particles, or WIMPs. When they collide, these particles would theoretically annihilate themselves, depositing heat into collapsing clouds of hydrogen and converting them into brightly shining dark stars. And the conditions for the formation of dark stars would have been just right a few 100 million years after the Big Bang, at the centre of dark matter halos. And this is when and where the first stars in the universe are expected to have formed. Fries says the new Webb observations have now identified spectroscopic supermassive dark star candidates, including the very earliest objects at redshift 14. Now, that's just 300 million years after the Big Bang. She says the dark stars would have had 1 million times the mass of our Sun. Such early dark stars are important, not only in teaching astronomers about dark matter, but also as precursors for the early supermassive black holes seen by Webb, which would otherwise be difficult to explain. In a 2023 PNAS study by Fries and colleagues, the first supermassive dark star candidates, JDES GSZ13-0, JDES GSZ12-0 and JDES GSZ11-0, were all identified using photometric data from Webb's near-infrared camera. Since then, spectra from Webb's near-infrared spectrographic instrument has provided additional data, allowing astronomers to identify the spectra and morphology of 4 of the most distant objects ever seen, including 2 candidates from that 2023 study. These include JDES GSZ14-0, JDES GSZ14-1, JDES GSZ13-0, and JDES GSZ11-0. Each is consistent with a supermassive dark star interpretation. JDES GSZ14-1 is not resolved, meaning it's consistent with a point source, such as a very distant supermassive star would be. The other 3 are all extremely compact and can be modelled by supermassive dark stars powering a nebula of ionized hydrogen and helium surrounding the star. Importantly, dark stars would have a smoking gun signature, an absorption feature at 1,640 angstrom due to the large amounts of singly ionized helium in their atmospheres. And in fact, one of the 4 objects analysed, JDES GSZ14-0, does show signs of this feature. Astronomers using ALMA, the Atacama Large Millimetre Submillimetre Array Telescope in Chile, measured the spectrum of the same object, revealing the presence of oxygen through a nebular emission line. The authors say that if both spectral features are confirmed, this object cannot be an isolated dark star, but rather a dark star embedded in a metal-rich environment. And that could be the outcome of a merger where a dark matter halo hosting a dark star merges with a galaxy. Alternatively, dark stars and regular stars could have formed in the same halo. The identification of supermassive dark stars would open up the possibility of learning about dark matter particles based on the observed properties of those objects, and would establish a new field of astronomy, the study of dark matter-powered stars. This is SpaceTime. Still to come, Australia's new lunar rover, and piecing together the early solar system. All that and more still to come on SpaceTime. Work's now underway on the Australian Space Agency ACE's first lunar rover mission, which is slated to launch before the end of the decade. The 20-kilogram four-wheeled robotic vehicle, called the rover, will be used by NASA as part of its Artemis program to study lunar geology, detecting rocks, craters and other phenomena of interest. It'll be launched as part of NASA's CT-4 Commercial Lunar Payload Services Initiative. Once on the moon's surface, the rover's expected to be operational for a full lunar day, that's equivalent to 14 Earth days. Scientists at the Queensland University of Technology are building the navigation systems for the rover. They're developing positioning systems that assist the semi-autonomous vehicle to safely explore the lunar surface with limited onboard computing power. The rover will be designed, built, tested and operated in Australia through a consortium of industry partners, research organisations and 10 Aussie universities, working in partnership with ASA, the Australian Space Agency. Once launched, it'll be remotely operated from an Australian Mission Control Centre and work alongside NASA in establishing a sustainable human presence on the moon. As part of the project, QIT's developed a new lunar test centre, which includes an enclosed test bed filled with a lunar regolith simulant designed to replicate the kinds of environment, surface conditions and lighting the vehicle will likely encounter during its time on the moon. This is SpaceTime. Still to come, piecing together the early solar system, and the constellation of the Southern Cross, the Magellanic Clouds, and 3 meteor showers are among the highlights of the October night skies on Skywatch. A new study suggests that from its earliest period, even before the last of its protoplanetary nebula gas had been consumed, the Sun's solar system and its planets, including the Earth, looked a lot more like a bin of well-used Lego blocks than slowly evolving spheres of untouched elements and minerals. The findings, reported in the journal Science Advances, suggest that far from being made of pristine material, the planets were constructed out of recycled fragments of shattered and rebuilt bodies. The study's lead author, Damanveer Singh Grul from Yale University, says the research paints a clear picture of the violent origins of our solar system. Scientists have long known that in the earliest days of the solar system, planets and protoplanets, known as planetesimals, formed through a combination of collisions known as accretion and core formation, which triggered chemical changes in the core's composition. But the level of influence of each of these forces has been unknown. Adding to the mystery, some planetesimals have unusual chemical signatures that would involve the presence of highly unlikely metals at the start of a naturally evolving core formation process. Grul and colleagues say the explanation lies with the smash and rebuild nature of the early solar system. For their study, the authors created simulations of how planetary cores developed in the early years of the solar system's formation, based on a reinterpretation of data taken from iron meteorites thought to be the remnants of the metallic cores of the first planetesimals. They hypothesized that high-energy collisions began between about 1 and 2 million years after the formation of our solar system 4.6 billion years ago. At that stage, some planetesimals had formed metal-rich cores, but the process wasn't complete. Collisions shattered these early cores, and their fragments later reassembled themselves into new planetary bodies through accretion. Grul says these events determined which elements and minerals young worlds carried to the next stage of planetary formation. The findings show that the pathway to planetary formation was far more dynamic and complex than previously thought. This is SpaceTime. And time now to turn our eyes to the skies and check out the celestial sphere for October on Skywatch. October is the 10th month of the year, and that may seem confusing since octo in Latin means 8 rather than 10. The answer lies in the old Roman calendar, which had just 10 months before the addition of January and February. And that 10-month year is still reflected today, with the name September or Septem being Latin for 7, October or Octo meaning 8, November or Novem 9, and December or Deci meaning 10. Of course, the highlight of October for kids and those who are young at heart has to be the last day of the month, celebrated as All Hallows Evening or Halloween. Halloween is based on ancient Celtic pagan festivals such as Samhain, the Gaelic festival of the dead. Samhain was eventually Christianized by the early church to become All Saints or All Hallows Eve, or simply Halloween. It's a time when darkness overtakes the light of day, a reference to the increasing hours of darkness as the planet's northern hemisphere moves towards longer winter nights. And so it's a time when the harvest comes to an end. The increased hours of darkness mean the boundary between the world of the living and the world of the dead becomes especially thin, allowing the dead and supernatural to rise in search of the living. And so the living wear disguises so as not to be recognized by the dead, and it's this which has led to today's tradition of the Halloween fancy dress party. In some parts of the world, cross-dressing is popular on Halloween, a reflection of the secret desires and fantasies of their pagan ancestors, sometimes not so many generations removed. To ensure that crops and livestock survive the cold winter months ahead, offerings of food and drink will be left outside for the spirits and fairies of the other side. And it was this which ultimately led to today's practice of trick-or-treat. Also, candles would be lit and prayers offered to the souls of the dead, as Halloween was a time when the spirits of the dead would return to their former homes. Special bonfires were also lit on Halloween to light the darkness, thereby preventing souls of the dead from returning and keeping the evil away. The flames, smoke, and ashes were deemed to have protective and cleansing powers and were used for divination. As for the tradition of carving pumpkins into jack-o'-lanterns, well, that was originally meant either to represent spirits or supernatural beings, or alternatively to ward off evil spirits. In many parts of the world, the Christian religious observances of All Hallows Eve include attending church services and lighting candles on the graves of the dead. and Christians historically abstained from eating meat on All Hallows Eve, a tradition reflected in the eating of certain vegetable foods on the day, including apples, potato pancakes, and soul cakes. Apple bobbing originated because the apple was a Celtic symbol of love, and so grabbing the apple with your teeth had certain erotic overtones. Halloween is a time of fortune-telling and divination games, playing pranks to scare people, visiting haunted attractions, telling scary stories, and of course watching horror movies. Looking to the southwest, you'll see the two bright pointer stars, which show the way to the Southern Cross. The brightest, and what also looks like the more distant of the two stars from the Southern Cross, is Alpha Centauri, which is actually the nearest star system to our own solar system. Alpha Centauri is a triple star system comprising two stars, Alpha Centauri A and B, which orbit each other in a binary, and a third star, Proxima Centauri, which orbit the pair. Like the Sun, Alpha Centauri A is a spectra type G yellow dwarf star. It's about 10% more massive than our Sun and about 1.5 times as luminous. Astronomers describe stars in terms of spectral types. It's a classification system based on temperature and characteristics. The hottest, most massive and most luminous stars are known as spectral type O blue stars. They're followed by spectral type B blue-white stars, then spectral type A white stars, spectral type F whitish-yellow stars, spectral type G yellow stars, that's where our Sun fits in, spectral type K orange stars, and the coolest and least massive stars of all are the spectral type M red stars. Each spectral classification is also subdivided using a numeric digit to represent temperature, with 0 being the hottest and 9 the coolest, and a Roman numeral to represent luminosity. Now you put all that together and our Sun becomes a G2V or G25 yellow dwarf star. Also included in the stellar classification system are spectral types L, T and Y, which are assigned to failed stars known as brown dwarfs, some of which were actually born as spectral type M red stars, but became brown dwarfs after losing some of their mass. Brown dwarfs fit into a unique category between the largest planets, which can be up to 13 times the mass of Jupiter, and the smaller stars, those spectral type M red dwarf stars we mentioned earlier. These can be 75 to 80 times the mass of Jupiter, or about 0.08 solar masses. Alpha Centauri A's binary partner, Alpha Centauri B, is a spectral type K orange dwarf star, a little smaller and cooler than its companion, with about 90% of the Sun's mass and about half its luminosity. This binary pair, Alpha Centauri A and B, orbit each other at between 11.2 and 35.6 astronomical units. An astronomical unit is the average distance between the Earth and the Sun, which equates to about 150 million kilometres, or around 8.3 light minutes. So the pair's orbit around each other varies by between the average distance between the Sun and Saturn and between the Sun and Pluto. It takes the two stars 79.91 Earth years to complete each orbit. On average, Alpha Centauri A and B are located 4.37 light years from the Sun. Now, although a light year sounds like a measure of time, it's actually a measure of distance. A light year is the distance of about 10 trillion kilometres. That's the distance a photon can travel in a year at the speed of light, which is around 300,000 kilometres per second in a vacuum and the ultimate speed limit of the universe. The third star in the Alpha Centauri system is a spectral type M red dwarf star named Proxima Centauri. Right now, Proxima Centauri is just 4.25 light years away, making it the nearest star to the Earth other than the Sun. It is only loosely gravitationally bound to Alpha Centauri A and B, orbiting the pair at an average distance of 13,000 astronomical units, or around 0.21 light years. That's about 430 times the size of Neptune's 30 astronomical unit orbit around the Sun. In 2016, astronomers confirmed the existence of an Earth-sized terrestrial planet orbiting within the habitable zone of Proxima Centauri, making it the nearest known extrasolar or exoplanet to Earth. The habitable zone, which is sometimes also referred to as the Goldilocks zone, is that area out from a star where it's not too hot, not too cold, but just right for liquid water, essential for life as we know it, to exist on a planet's surface. The planet, known as Proxima b, takes just 11 Earth days to complete one orbit around its host star. That's far closer than Mercury's 88 Earth day orbit around the Sun. A few years ago, a second, more distant planet, Proxima c, was also discovered orbiting around the star, but well outside its habitable zone. The second and slightly fainter of the two pointer stars is Beta Centauri, and while Alpha Centauri is the third brightest star in the night sky, outshone only by Sirius and Canopus, Beta Centauri is only about the 10th brightest. Looking to the southeast, and you'll see the bright blue-white star Alpha Eridani or Achernar, which represents the southern tip of Eridanus, one of the largest and longest constellations in the sky. Achernar is located about 139 light-years away. It's actually a binary star system comprising two stars, Alpha Eridani A and Alpha Eridani B. Alpha Eridani A is a hot young spectral type B blue star. It has about 6.7 times the mass of the Sun and a stunning 3,150 times the Sun's luminosity. By comparison, the companion star Alpha Eridani B appears to be a spectral type A white star with about twice the Sun's mass. The two stars orbit each other every 14 to 15 Earth years at an average distance of about 12.3 astronomical units. Because of its high rotation rate of over 16 kilometers per second, Alpha Eridani A is actually one of the least spherical stars in the Milky Way, spinning so rapidly it's assumed the shape of an oblate spheroid, with an equatorial diameter 56% greater than its polar diameter. This distorted shape means the star displays a significant latitudinal temperature, with its polar temperature being about 20,000 Kelvin, while its equatorial temperature is only around 10,000 Kelvin. That's because it's much further away from its stellar core. The high polar temperatures are generating a fast polar wind. That's ejecting matter from the star and creating a spectacular polar envelope of hot gas and plasma. Now, if you look up between the South Celestial Pole and Achernar from a really dark place, you'll see two faint fuzzy-looking clouds. Now, these aren't actually clouds. They're two satellite dwarf galaxies which orbit the Milky Way, known as the Large and Small Magellanic Clouds. They're named after Ferdinand Magellan, who became the first European to officially record them during his expedition to circumnavigate the Earth between 1519 and 1522. The bigger and nearer of the pair is the Large Magellanic Cloud, which is located around 160 light-years away. It's easy to spot about halfway between Achernar and the horizon. It's about 14,000 light-years across, twice that of the Small Magellanic Cloud, which is located a more distant 200,000 light-years from the Milky Way. Now, by comparison to these two satellite galaxies, the Milky Way is huge, 100,000 light-years across. These two dwarf galaxies are separated from each other by roughly 75,000 light-years. The Magellanic Clouds were considered the closest galaxies to the Milky Way until the 1994 discovery of the Sagittarius Dwarf Elliptical Galaxy and the 2003 confirmation that the Canis Major Dwarf Galaxy is actually our nearest galactic neighbour. The total mass of the Magellanic Clouds is uncertain. Only a fraction of their gas seems to have coalesced into stars. They also probably both have very large dark matter halos. Still, one recent estimate places the total mass of the Large Magellanic Cloud at about 1/10 that of the Milky Way. The Magellanic Clouds have both been greatly distorted by gravitational tidal interactions as they're gradually torn apart and absorbed by the Milky Way. These huge tidal forces have turned both Magellanic Clouds into irregular disrupted barred spiral galaxies. The Large Magellanic Cloud still retains a very clear spiral structure, at least in radio telescope images of neutral hydrogen. But gravity isn't a one-way street, and the combined gravitational force of both Magellanic Clouds is also affecting the Milky Way, distorting the outer parts of our galactic disk. And there are streams of neutral hydrogen gas clouds and isolated stars, connecting both dwarf galaxies to each other and to the Milky Way. A brilliant example of galactic cannibalism at work. Now, if you look just above the Small Magellanic Cloud using a backyard telescope or a good pair of binoculars, you'll see a small blurry dot. That is the 47 Tucanae globular cluster. A tightly packed ball of stars some 16,000 light-years away, they were all originally formed at the same time through the gravitational collapse of the same molecular gas and dust cloud. If you look to the west, you'll see the bright reddish-orange supergiant star Antares, the heart of the constellation Scorpius the Scorpion. And above it, you'll see a bunch of stars stretching out, shaped like a reverse question mark. That's the tail of the Scorpion. Now, just above and to the north is the constellation Sagittarius the Archer. Sagittarius shows the way to the supermassive black hole at the centre of the Milky Way galaxy, some 27,000 light-years away. This monster black hole, known as Sagittarius A star, has about 4.3 million times the mass of our Sun. Now, looking to the north-northwest this time of the year, you'll see the constellation Lyra the Harp, and its brightest star Vega, the fifth brightest star in the night sky, and one of the closest at just 25 light-years away. Vega is a spectral type A white star, more than twice the size and some 40 times the mass of our Sun. Now, just to the right of Lyra, and almost directly north just above the horizon, is the constellation of Cygnus the Swan, and its brightest star Deneb, one of the most luminous stars in the sky. Deneb is a massive spectral type A white supergiant, some 19 times the mass and over 100 times the diameter of the Sun. The star is somewhere between 55,000 and 196,000 times as luminous as the Sun. The huge range in luminosity estimate is caused by the difficulty in determining Deneb's exact distance from us. Science's best estimates place it somewhere around 2,600 light-years away, give or take 212 light-years. High in the northern sky right now is the constellation Aquila the Eagle, and its brightest star Altair. Altair is another spectral type A white star, but located a lot closer, just 17 light-years away. It's about 10 times brighter than the Sun, with about 1.89 times the Sun's mass. Despite its size, Altair spins on its axis in just 10 hours, compared to our Sun's 28 Earth day rotation. Now, these three stars, Altair, Deneb and Vega, form a stellar grouping known as the Summer Triangle. Now, also in October, there are three meteor showers: the Draconids, the Taurids and the Orionids. The Draconids take place on October the 8th. They're so named because their meteors appear to radiate out from the constellation Draco the Dragon, and so are best viewed from the northern hemisphere. They're actually produced as the Earth's orbit takes it through the debris trail left behind by the comet 21P Shihokubini-Zinna, which takes about 6.6 Earth years to make a single revolution of the Sun. The Taurids meteor shower takes place on October 10th, and as their name suggests, they appear to radiate out from the constellation Taurus the Bull. Their meteors are composed of larger-than-average pebbles and dust grains, and are thought to be generated by debris left behind by the comet 2P Encke. Although it's thought that both the Taurids and Encke could be the remains of an earlier comet which disintegrated over the past 20,000 to 30,000 years, breaking into several pieces and releasing material both by normal cometary activity and possibly also by gravitational tidal interactions with the Earth and other planets. The Taurids debris stream is the largest in the inner solar system, taking the Earth several weeks to pass through and resulting in an extended period of meteor activity compared to other meteor showers, which are usually over in just a matter of days. Now, due to the gravitational perturbations of the planets, especially Jupiter, the Taurids have been spread out over time, allowing separate segments, labelled the Northern Taurids and Southern Taurids, to be observable at different times in different hemispheres. The Southern Taurids are active from around September the 10th to November 20th, while the Northern Taurids are active from October the 20th to December the 10th. The third meteor shower this month is the Orionids, which peak on October the 20th. They're caused by debris from the comet Halley, which also causes the Eta Aquarids meteor shower in May. Comet Halley takes 76 years to complete each orbit around the Sun. It'll next become visible near Earth in 2061. The Orionids are equally spectacular in both northern and southern hemisphere skies, with up to 20 meteors an hour radiating out from the constellation Orion. The best time to see the Orionids is just after midnight and right before dusk. This is SpaceTime. And that's the show for now. SpaceTime is available every Monday, Wednesday and Friday through Apple Podcasts, iTunes, Stitcher, Google Podcast, Pocket Casts, Spotify, Acast, Amazon Music, Bytes.com, SoundCloud, YouTube, your favourite podcast download provider, and from spacetimewithstuartgary.com. SpaceTime's also broadcast through the National Science Foundation on Science Zone Radio and on both iHeartRadio and TuneIn Radio. And you can help to support our show by visiting the SpaceTime store for a range of promotional merchandising goodies, or by becoming a SpaceTime patron, which gives you access to triple-episode commercial-free versions of the show, as well as lots of bonus audio content which doesn't go to air, access to our exclusive Facebook group, and other rewards. Just go to spacetimewithstuartgary.com for full details.
You've been listening to SpaceTime with Stuart Gary. This has been another quality podcast production from Bytes.com.